So now we look at the lemma that if x and y be normed spaces and x is finite dimensional, then every linear transformation from x to y is bounded. Now let us break this proof into three parts. So first we have our x space, okay, and we know that x is finite dimensional, okay, finite dimensional, which means that every element belonging to my norm space capital X has a unique representation. I wrote it in the form of the basis vectors. So let E1 to En be the basis for X, which means that every element X belonging to my norm space has a unique representation. This is linear algebra 101. So every element in my norm space can be written as a linear combination of the basis vectors. And now I introduce a norm. The norm is defined like this. And when I need to show that t from x to y is bounded, all I need to show is that the norm of t is less than some constant. And the way I do it is I first define a norm on x, and I say that I write my t of x like this. So how can I write t of x like this? It's simple. Let's break it down. You can write it as t times of sigma alpha I ei. Now I am putting the t inside because this t is linear, and we saw in the previous videos that if my t or if my operator is linear, I can do all these kind of tricks. I can put my operator inside t ei in this I equals to 1 to n. I equal to 1 to n, I equal to 1 to n. And now from this step, I can get this step very easily. There is no magic happening from this step to this step. But now when I have to go from here to here, I need to make use of an inequality. It's called Cauchy-Schwarz inequality. So essentially what Cauchy-Schwarz inequality says is this, that sigma of eta, neta, I ranging from 1 to n is less than or equal to under root of sigma k equal to 1 to n psilon k whole square, and sigma m equals to 1. Well, this is applicable from I equals to 1 to infinity also, so I would change it like this. Rather than n, it's infinity now. Infinity, and here I can write again neta I to the whole square. So this is the, we are going to use this inequality many times in our analysis, so it's important to know the exact name of this, that from the next time I would just say that from Cauchy-Schwarz inequality in equality. So we got from here to here, and now I know that this thing was my norm of x. So I see that, what do I see here? What do I see here? I see that, okay, what do I know of? I know in life that norm of tx is less than norm of t times norm of x, and now we already have norm of x. So my norm of t should definitely be less than this quantity. And this is exactly how I prove that t is bounded, because if you remember, if t is less than some constant, then t is bounded, and as we can see here, t is less than this. So of course my operator t is bounded. So now we are going to discuss a very beautiful proof in function analysis, and it goes something like this. So if I have, let me put it like so, if X is a normed space and Y is a Banach space. Let me draw. I really like to draw diagrams. I don't know if they're of any help to you, but just for the sake of it. So this is Banach space and this is normed space. And now what we have is that there is an operator which takes my elements from the normed space to the Banach space, and we say that T itself lies in the space Lxy, which is the space of all bounded functions from x to y, and I say that this space is a B space, a Banach space. So this is what I need to prove, okay? And this is how we proceed towards it. So let Tn be a Cauchy sequence in Lxy. Lxy is again the space in which my operator lives. Okay. Now, if there is a Cauchy sequence in Lxy, it follows that Tnx is a Cauchy sequence in Y for each fixed x belonging to x, because so in order to understand this line, what we need to do is go back to the concept of what a Cauchy sequence is. So if I have a Cauchy sequence Tn, it means that for every epsilon greater than 0, there exists a n belonging to my natural numbers. So this n is different, and this n stands for natural numbers, and this is just one natural number. So if I draw these two lines, it means the set of natural numbers. And now I write that, okay, if epsilon, for every epsilon greater than 0, there exists a number such that the norm of Tn minus Tm is less than epsilon. This was the condition for Cauchy condition, you know. This is how I define a Cauchy sequence. And now I know that if Tn is a Cauchy sequence, then I can write this Tnx minus Tmx like this. We just discussed in a few minutes ago that how I can break my operator into two pieces. And now I can, so we discussed previously that I can do this operation. I can take the t out since my t is linear, so I can write it at like this. And now I know that this Tn minus Tm is less than epsilon. So Tnx minus Tmx is less than this epsilon times norm of x. Therefore, Tnx is Cauchy. So now I know that my space Y is complete. And what happens when I have a complete space? It means that if I have any Cauchy sequence, then this Cauchy sequence converges to a point which lies in my space Y. Let me put it this way. So the limit n tending to infinity Tnx is equals to Tx, and this Tx lies in my space Y. Tx belongs to space Y. This is what I meant when I say that my space Y is complete. I take any Cauchy sequence, I take the limit of it, and the limit lies in the set. Now I denoted this limit by Tx, and therefore we have defined a function T from my space, norm space X, to my Banach space Y. And here I prove that my T is linear. How do I prove that? I write it down at like this. So I replace this T with limit n tending to infinity Tn, because this is exactly what we did before. And since my Tn is linear, I can take this T inside and put the alphas outside. And now I know that limit n tending to infinity Tnx1 is nothing but Tx1, and limit n tending to infinity Tnx2 is nothing but Tx2, because Tn tends to t. And therefore, I see, if I look at this and this, I see that my operator t is linear. Now, what do I need to prove? Now I need to prove that my operator is bounded, because ultimately what I need to prove is that t belongs to Lxy, which is the space of all bounded functions from x to y. So how do I prove that my t is bounded? I start by choosing an epsilon greater than 0. And again, since I took a Cauchy sequence, I have this condition satisfied. This is exactly what I wrote here. This condition. Because I took a Cauchy sequence, and now I chose my x belonging to my norm space X such that the norm of my small x is equals to 1. So here, if my norm of x is equals to 1, then Tnx minus Tmx is less than epsilon, which is exactly what's written here. And I take the limit n tending to infinity this time. So rather than writing Tmx, I write Tx. And now I can say that I just add and subtract one term. So we've skipped a step here. Let me write that missing step down. So if I have this, then I subtract Tmx plus 1 x, I add t. The indices here might confuse you a bit, but when you are doing these proofs, there's just one idea you need to remember, and that is, it's not necessary to understand each and every part of the proof. What really matters is to understand the idea behind the proof. So if you understand the story flow, if you can follow the story, then it is of more importance to you, because proofs and the minute details and tricks is something that you can figure out at any point. But if you get the main storyline of the proof, then that's what really matters. So again, back to the point. So I add and subtract this term, and then from triangle inequality, I write it down as two terms, and that's why the less than or equal to sign. And again, I saw that this thing was less than epsilon here. And again, this thing is less than epsilon as n tending to infinity. So this Tnx minus Tx is less than 2 epsilon. And now if we remember how we defined our notion of the norm of an operator, it was norm of t is equals to the sup norm of x equal to 1 Tx for every value of x belong to capital X. So this is how I define my norm of t. So similarly, my norm of Tn minus t is defined in the exact same way. I take norm of x equals to 1, I replace everything here, and this, as we saw before, is less than 2 epsilon, which means that the norm of Tn minus t is bounded by this quantity, which implies that this Tn minus t belongs to Lxy, which is the space of all bounded functions from x to y. So if Tn minus t belonging to Lxy, and Lxy is in fact a vector space, so if a minus b belonging to Lxy, then of course a minus b also belongs to Lxy, which implies that this is exactly what's written. So since it satisfies the rules of vector space addition, my t also belongs to Lxy, and moreover from star, so this is star, we see that Tn tends to t because so you give me any value of epsilon, then I can find a value of n such that this difference is less than 2 epsilon. So this was the exact condition for converging sequences, that if I have any value of epsilon greater than 0, I can find a value of n such that the difference between Tn minus t would be less than epsilon. This means that Tn tends to T. This is what I wanted to prove in the first place. So I know this is a bit of a technical proof, so let's break it down and summarize it again. So what I wanted that if X is normed space, Y is a Banach space, then the operator taking elements from the normed space to the Banach space itself lies in a Banach space, and this is the Banach space of all functions, all bounded functions. This is what I want to prove, that T lies in the space of all bounded functions. And how do I prove that? I take a Cauchy sequence. I show that this Cauchy sequence converges to a limit point. Then I show that my T is linear. Then I prove that this quantity Tn minus T is bounded. And once I show that, I can say that my Tn minus T lies in the space of all bounded functions. And since this is itself a vector space, I can say that T also lies in it and that my Tn converges to T.